Okay, I'm going to go ahead and get started so we don't waste too much time. Welcome to Our Medicine. I'm pleased today to be introducing Dr. Ziad Obermeyer, who will be speaking on reinventing medicine with AI. Dr. Obermeyer is Associate Professor and Blue Cross of California Distinguished Professor at UC Berkeley. He teaches at School of Public Health and was a founding member of the Berkeley UCSF Joint Program in Computational Precision Health. His research uses machine learning to help doctors make better decisions and help researchers make new discoveries by seeing the world the way algorithms do. His work on algorithmic racial bias has been highly influential in shaping how healthcare organizations and policymakers hold AI accountable, from work with state attorneys general to testimony before the Senate Finance Committee. He is a co-founder of Nightingale Open Science and Dandelion Health, a Chan Zuckerberg BioHub investigator, and a research associate at the National Bureau of Economic Research. He was named one of the 100 most influential people in AI by Time magazine. Previously, he was assistant professor at Harvard Medical School, and he continues to practice emergency medicine in underserved communities. Ziad, welcome.
Thank you so much. This is such a treat to be here because I feel a lot of connection to the community of people who are using data in the way that you all do. Looking forward to chatting. And apologies for the somewhat grandiose title of this talk, but I hope that the general message will resonate with you. The place I want to start is by giving a caricature of my view of the current pathway for producing medical discoveries. And the way I would describe it is we basically start by choosing some biological space. And that can be the space of genes or proteins or signaling pathways or lots of other things. And then typically what happens is we pick our favorite gene or protein or pathway, and we show in elegant bench experiments that it seems to work to have some effect on a target. Like it reduces some measure of inflammation, it reduces cancer progression rates, et cetera. So all of that's done at the bench. And then slowly that trickles up to animal models, and the animals get bigger and bigger until finally we get to a clinical study where we try to show that the drug that changes this target actually has the clinical effect that we hope it does. And so this is, I think, again, a simple version of the current way we do medical discovery, moving from bench to bedside. And I think, if you look at pharma companies or NIH or even a lot of the activity in the AI space, we're basically all in on this model. And this model works really, really well for some problems. And I think the way I've tried to make sense of the kinds of problems it makes sense for is when your problem is at the genetic level, then working at the genetic level is obviously the right approach. And I think that's true for a lot of cancers that are driven by specific mutations that we now have amazing targeted therapies for. A lot of immunological problems actually are you can shut them off by shutting down one pathway. And so I think that, there are a ton of huge successes going back to the 80s all the way to mRNA vaccines that show that this model is really, really good for a bunch of problems. It's not good for 100% of problems. And those are the problems that I'm most interested in because we've got a lot of resources going into this pathway. And historically, there's been another pathway that has driven a lot of discoveries, but over the past 20 to 30 years, I'd say that pathway has largely lain dormant. And so I'm going to talk to you about two problems where I think we can reboot that pathway, drawing on some of the recent progress in artificial intelligence tools, and really make some progress on these things that have proven pretty resistant to molecular approaches. And the first problem I'm going to talk to you about is pain. And I think pain is really emblematic for me of the failures of our current approach. And I think, I'm going to focus on knee pain. It's one of the places in the body that hurts the most, along with the back. But I think when you read the literature on knee pain, it's almost like you're not in the knee because this is a representative illustration here from a a really nice review article on the current state of our understanding about knee pain. And you can see that there's this kind of caricature of a knee, but pretty soon you're zooming all the way into this joint space and you're looking at matrix metalloproteases and TNF alpha and things like that. And so we've really zoomed down to a very, very low level of abstraction. And I think levels of abstraction are a useful way to think about this because they're just different ways of thinking about the same thing. So when you think about a computer, you can think about a computer as a collection of transistors. You can think about it at the level of machine code, all the way up to languages like R, and then user interfaces. And each of those levels is kind of like its own thing. And problems that look really, really complicated on one level actually have a great solution that's quite simple on another level. And so choosing that right level of abstraction is really, really important. And I think one problem with choosing this level of abstraction for pain and trying to bring the cures up to the bedside um, is, well, there are two problems. One is that we still have a lot of people in pain, so the problem has not been solved. And I actually think you can draw a pretty clear line from a molecular approach to pain to the opiate epidemic that we ended up with. Because, as someone who practiced for a while in the emergency department and saw a lot of people with pain, we often don't really get to the bottom of what's causing the pain. And when your final diagnosis is pain, what's the treatment? Well, it's opioids. It's treating the pain. Um, so so if this is the current state of affairs, I want to actually go all the way back to when people first started studying pain in what I view as a modern way, which was in the 1930s and 40s, where there were these classic studies of researchers like Doctors Kellgren and Lawrence, who just started doing X-rays on people. So X-rays were, diffusing pretty rapidly, but they were still a new technology in that era. And what these guys did is they just went to a coal mine where you had a lot of people in pain, and they just started x-raying people wherever it hurt. So they x-rayed a lot of backs, a lot of knees, and they didn't even really know what they were looking for. They just started doing x-rays. And they found a lot of things that seemed to correlate to pain. And so what they did is they were looking at the x-rays of coal miners who had a lot of pain and comparing them to the contractors and office workers that were working in that same coal mine, but had a much less demanding job. And they were finding the things that corresponded to pain and to the kinds of injuries that people were having. And the definition that they produced of osteoarthritis based on x-rays is still actually what we use today to define arthritis in clinical studies. So that's the old approach. And I think, here's again a caricature of that approach is rather than starting at the bench with a molecule or a gene or a protein, this research started at the bedside. And what it did in the case of x-rays, quite literally, was to take a patient who was alive and had problems and a story and a history and injuries, and basically project that patient onto some space, X. And then what they did was they looked at that projection, the X-ray, and they defined a problem with some human function. So h of x, and that's still, the definition we use today. So it was a human looking at this machine-generated data about a patient and trying to make sense of it. And then translating that into abstractions like osteoarthritis or, correlating it to injuries and thinking about strain or things like that. And so you'll notice that this is working at a much higher level of abstraction. So this is at the level of anatomy and physiology rather than at the level of molecules. And I think that's just an important distinction to make. It starts at the bedside, and because it starts there, it stays at that higher level of abstraction than we're currently working on today. Now, I don't want to romanticize this model too much because even though they tried to develop understandings based on that problem, we still have a lot of people with pain, and that's why we ended up going down the molecular approach to pain because this wasn't enough. The other problem with this approach is that there were a lot of anomalies, and let me tell you about one. Um, it became pretty clear once people started doing studies of diverse populations, unlike the populations in the coal mine that Kellgren and Lawrence originally studied, that there were some puzzling findings, especially with respect to Black patients. And so one of the very salient findings was that Black patients had much more pain, even when you condition on the Kellgren-Lawrence grade. So the Kellgren-Lawrence definition has grades from 0 to 4. And when you looked at Black versus white patients who had the exact same Kellgren-Lawrence grade, Black patients had extra pain, even when you took the degree of osteoarthritis into account. So that gap was very puzzling. And it didn't seem to be explainable on the level of abstraction of the knee and the X-ray and the anatomy and the physiology. And so what people very reasonably did was they moved up a level of abstraction or two to psychology and social science. And so a lot of the research that tried to explain this pain gap between Black and white focused on stress or psychosomatic translation of mental anguish into physical pain, or looked at things like differential access to care, which could also produce that finding of more pain conditional on X-ray findings. Because if you've got a great physical therapist and access to a lot of stuff, you're going to report less pain. And all that research, I think, is very, very legitimate and good. But I would say that all of that research forgets one important source of pain, which is the knee. And rather than trying to find explanations in different levels of abstraction, I think another hypothesis is that humans just aren't that good at making sense of really complicated data, like an X-ray. And it's very possible that in those initial studies that still drive our understanding of arthritis today, they might have missed something. And in particular, they might have missed something that's much more common in Black patients because they didn't have any Black patients in that original set of studies from the coal mine. And that problem, if there are findings that are more common in Black patients that cause pain, or any kind of patients for that matter, you're going to get that same empirical fact of, oh, these patients have more pain than I can explain with the X-ray. But it's not about those patients, it's about your interpretation of the X-ray. This reminds me of another place where choosing the right level of abstraction is quite important. Because for a long time, when doctors were confronted with the problem of gastric ulcers, they actually went up to a very high level of abstraction, just like people do with knee pain or other kinds of pain. And they tried to find explanations in personality types. So, like the type A personality. People talk a lot less about the type B personality, but that's the other personality. And this was thought to be the cause of peptic ulcer disease until a new measurement technology and endoscopy actually revealed that it was a bacterium and you treat it with antibiotics, not by managing your stress. And so that's another example of how problems that look really messy and complicated and unclear at one level actually have a really easy solution once you start looking at the right level. Okay, so back to the knee. You probably know where this talk is going. Could AI help to find stuff in the knee X-ray that the original studies missed? And I would say, yes, it can, as I'll try to show you, but not if we do what most people unfortunately do when they're trying to teach an algorithm to read an X-ray. And the common playbook today is to get a bunch of X-rays and then get a bunch of radiologist interpretations of that X-ray and teach the algorithm to go from the X-ray pixels to the text of the radiologist's report. It's a very convenient label, and that actually has a lot of uses, which I think are great. But it's not going to solve this problem because when you automate what the radiologists are already looking for, you're not going to find anything that the radiologists are missing. And if we want to find an explanation for that pain gap, conditional on what the radiologists are seeing, teaching the algorithm to automate the radiologist is not going to do that. I think one reason that a lot of people follow this playbook of human interpretation from X-ray pixels is that those data are comparatively easy to get because they all live in the PACS system of the hospital, and it's a lot harder to find data on patient pain scores. But if you do, you can actually have a very different approach. So if that common approach today is learning from the radiologist and mapping from X-ray to Kellgren-Lawrence grade or some other human interpretation, another strategy is to listen to the patient and map from the X-ray pixels to the pain score that that patient is going to report. And so that's what we did in this work that was led by my colleague Emma Pearson at Berkeley a few years ago. And we drew on this really, really nice NIH-funded longitudinal study of knee pain that was quite diverse, that linked X-rays not just to the radiologist's interpretation, but to the patient's pain score. And once you have those data, it's very easy to train an algorithm that just predicts the pain score from the X-ray. And there's a really nice empirical test built into this result, which is that if there's this common belief that, oh, when people report their pain score, it's super noisy. And it really has much more to do with what they had for breakfast or what mood they're in or whatever than anything about the knee. But if we can predict the pain score using just the pixels in that knee, then there's something in that knee that can explain the pain score, and it's not noise by construction because you can't predict noise. And that also is a clue, if we can make that prediction work, that level of abstraction of the X-ray is quite a useful one for making progress on this problem. And so let me show you maybe the main finding from this result, from this paper, is that in this study, if you look at the unconditional difference between black and white patients in average knee pain, it's huge. The scale is a little bit counterintuitive, that no pain is at 100 and severe pain is less than or equal to 86. I do not know how they chose the scale. But on that scale, the average difference between black and white patients is 11 points. So it's more than halfway from no pain to severe pain. If you control for KLG, you do account for some part of that gap, so about like 9% of that gap. But if you control for the algorithm's predicted pain score, you get rid of almost half of that gap. And the algorithm isn't just reconstructing things that we already know are correlated to pain, because we can control for those directly. So we can control for BMI, we can even control for actual race. The study site, maybe it's reading differences in X-rays based on machines, and that's correlated to pain. None of that actually changes the ability of that algorithm score to predict pain. Instead, the algorithm is actually finding new signal in that X-ray that explains pain, and those findings are more common in black patients than in white patients. One implication of this, by the way, is that there's this other puzzle in the literature, which is that even though black patients have much more knee pain, they get far fewer knee replacements, even when you control for insurance and access to knee replacement. And this could be one of those things that's driving that disparity, is that to get a knee replacement paid for by insurance, you don't just need to have knee pain. You have to have knee pain and a radiologist say that you have severe arthritis. And if black patients have severe arthritis, but the radiologists are not seeing on the X-ray because they're not looking for these findings that were omitted from that original score, you would actually end up with a lot fewer patients with knee pain being referred on to the orthopedic surgeon and maybe getting referred to a therapist instead. So this, I think, is just one example of the things that I'm working on in my lab alone, of where AI can really help go back to some of these basic things that are foundational in medicine, but that we haven't refreshed in a long time. So in this setting, this score from 1952 based on middle-aged white men can actually be improved for everybody by learning from a large, diverse cohort of patients and their pain reports. Our algorithm actually predicted pain better for everybody, but that improvement was particularly noticeable for black patients who weren't in the original studies. If you think about what PCR does, PCR also produces a piece of raw data, which is the amplification curve of the target genetic sequence over time. Today, what humans do when we interpret PCR tests is we just say, okay, well, did it end up over or under a threshold? But in work that's being done by one of my PhD students at Berkeley, Hung Vu, she's training an algorithm to learn what positive and negative curves look like as a whole, not just a threshold. And it turns out that thresholds actually, there's no one threshold that can perfectly discriminate positive from negative curves. And so adding in that information from the shape of the curve over time can really, really help discriminate between people who have, for example, COVID or other infections and people who don't. Another PhD student at Berkeley, Alex Schubert, is actually working to train an algorithm on the electrocardiograms of patients who come into the ER with a symptom that could be heart attack, and looking at their catheterization results and showing that all of the things that I memorized in medical school to diagnose heart attack are actually not that great for predicting who ends up with a lesion on their catheterization and finding new signs of heart attack in the ECG that doctors don't currently look for. So there are lots and lots of things where this playbook can really, really help to refresh and reboot some of these fundamental things that are part of medicine, but that we haven't looked at empirically in a pretty long time. Okay, so in this knee example, I think a really common question that I wonder about too is what is the algorithm seeing? Like what can it and so if you think about what we did in this framework of bedside and bench, we projected the patient onto the X-ray as Callaghan and Lawrence did. But instead of looking at it as humans, we had an AI pain predictor that just went from the X-ray to the pain score of the patient. And I think a natural next step that we actually did is to run this playbook of like generating a heat map of like, well, where is the algorithm looking on the knee? So you basically kind of randomly permute some pixels and you see how the prediction changes. And that can give you a sense of which pixels are important for driving that prediction. So we did that, and what you see is that, like, the pixels that seem important are, this is a knee, this is the femur, if I'm remembering correctly, this is the tibia, the fibula, this is the joint line where the knee flexes. And the algorithm seems to be, quote unquote, looking at the joint line, which seemed good. It's like, okay, it's not looking at the corner of the image, it's not looking at some weird text or something like that. And so I think one consequence of that is like, okay, great. So basically the molecular playbook is probably right, because that takes us right back to like, okay, let's just that the problem seems to be here where the cartilage and the joint fluid lives. So let's just keep looking at those inflammatory markers and cartilage degradation and things like that. Um, and I think the problem with that interpretability playbook is in many ways the same problem that doctors have. And the reason that a lot of people end up getting much better results from chiropractors and physical therapists, which is that imagine a model where, of course, people get osteoarthritis, but there's a natural variation in the angle at which everyone's femur comes out of their hip. And if that angle is wider, the vector of gravity is going to be a little bit shifted towards the inside of the knee, the medial knee. And if your angle is a little bit more in, it's going to be shifted outward. And that model turns out to be a very good model that predicts where osteoarthritis develops, just based on a very simple physical understanding of where the forces are loading in the knee. Now, if you believe that model, that like there's this three vector thing connecting the hip and the knee and the ankle and the force of gravity, what would the heat map look like? Would you ask the algorithm, where is it looking, and would it find this vector? No, the algorithm would actually look exactly like the picture that we drew, which is that what explains the pain? Well, it's the cartilage. But why is that cartilage messed up? It's because of this correlation between the hip and the ankle and the knee and all these other things. But the algorithm, just like the doctor, is going to focus on the component that failed, because that is the most tightly correlated with the patient's pain score. And it's not going to recover anything about the quote unquote true model that produced that problem to begin with. And so I think rather than asking AI to basically do it for us and tell us what it's seeing, I actually think a much better model is having the AI system help us to see. And so rather than trying to process the image ourselves with our human eyes and cognition, we can actually use AI to do massive quantification of these images, not just of this simple three vector model of the knee, but of every single muscle compartment, of all of the angles of attachment and torques. And that can help us see things like strain and weakness and asymmetry that we actually can't really see unaided because it's too complicated. And that can in turn produce models of understanding things like knees that can give rise to new hypotheses about how to fix it. And so I think that this is a model that I'm playing around with clinically right now of going from these quantification exercises of images all the way back to experimenting with individual patients and seeing if we can solve their problem as an empirical test of that understanding. Okay, let me stop there. I have my Q&A open, so please drop questions in there and interrupt me if that's allowed. But I'm going to go on to the second problem that I wanted to talk to you about, which is sudden cardiac death. So I remember learning about this in medical school and just being floored by how many people just drop dead with no warning. So in the US alone, it's like hundreds of thousands of people. And it's really hard to study because by the time you know who you should be studying, it's too late to really study them. And if I were editorializing a little bit about the research in this field, I'd say that there's a certain lack of curiosity. Because when you ask people like, well, what's going on? And most people are like, well, it's like usually it's like a big heart attack. And you're like, yeah, but these people are pretty healthy. Like most of them actually don't even have a history of heart disease or atherosclerosis. Like they're pretty low risk. And the explanation is like, yeah, sometimes your first heart attack's really big. Um, but I've always found these explanations kind of unsatisfying. And I think what makes this whole situation even worse is that we actually have the solution to this problem. So if you knew somebody was going to drop dead from an arrhythmia, you would put in a defibrillator to detect and terminate that arrhythmia before it kills them. We're just very, very bad at matching those defibrillators to the right patient. So uh, evidence exhibit A, people drop dead without defibrillators all the time. Exhibit B, when we follow along the defibrillators the doctors do put in, the majority of them actually never fire because the person never has the arrhythmia that we thought they were going to have. And so we're wasting a lot of defibrillators at the same time that we're missing a lot of people. And so it'd be really, really useful to predict who needs one of these things. And so what we do is something pretty simple. We have a collaboration with a Swedish region, like a regional healthcare system. And we just get all of their EKGs that were done over a multi-year period. And the nice part about doing this in Sweden is you can link those ECGs to all of the death certificates and get the cause of death and the location of death. And so we just predict who is going to have the epidemiological definition of sudden cardiac death. So death outside of the hospital from a cause that is either unknown or cardiac. And we train a model to just predict that thing. And it works pretty well. So this is a graph that shows you the rate of sudden cardiac death in the high-risk group as you change the threshold for defining the high-risk group. So if you look at the far right, the rightmost point on this graph is the top like 0.4% of patients, and those people have a rate of about 10% in the year after they get their ECG of dropping dead, which is a pretty high risk considering the gravity of that outcome. If you define a high-risk group that's based on how we enroll people for clinical trials based on their risk, you come up with about 2% of the population that's high risk at this threshold, and they've got a sudden cardiac death rate of 6% per year. By comparison, if you look at what doctors are currently using to predict this, which is it's a metric derived from a cardiac ultrasound called left ventricular ejection fraction. That's also about 2% of the population. Those people die at around 4.4% a year. So we're finding people who, number one, have a higher risk than the people that doctors are currently putting defibrillators into. But maybe more importantly, 80% of our high-risk group does not have low left ventricular ejection fraction. And so these are new patients that we don't currently know about that might benefit from a defibrillator. Now, just because you can predict sudden cardiac death doesn't mean you can prevent it. But one of the things that made us much more optimistic that these were preventable deaths is that we could also look at the rate that people were diagnosed with these arrhythmias. Sometimes these arrhythmias self-terminate, and a doctor is lucky enough to catch them on an electrocardiogram. And so that's the purple line there. And that rate at which people develop arrhythmias also goes up quite steeply in predicted risk, although not as steeply as the rate at which people just drop dead. And that's true in Sweden, but it's also true in a cohort from San Diego, where we're able to just take the model directly from Sweden, drop it into San Diego, and make predictions with no fine tuning. And we find that people have this steeply increasing rate of these fatal or near fatal arrhythmias over time. We can also take that algorithm into a detailed cardiac arrest registry in Taiwan and show that it's much better at discriminating arrhythmic deaths from controls than it is at discriminating non-arrhythmic cardiac arrests from controls, which also gives us some additional confidence in the model's ability to predict in lots of different settings. And finally, I know it's a violation of etiquette to show regression tables in a talk, and I ask for your forgiveness, but just focusing on the red number, if we look at people who have defibrillators implanted in our Swedish sample for other reasons, of course, doctors don't know about our risk score, but sometimes people just get defibrillators because doctors see something else. If we look at the high-risk patients, according to our model, who get a defibrillator, and we compare them to the people who are high risk who didn't have defibrillators, the people with defibrillators die a lot less than the model predicts. And when we replicate that analysis with the traditional metric of left ventricular ejection fraction, we actually get similar numbers, analogous numbers to the randomized trial effect sizes that are showing the effect of defibrillators in the high-risk patients for left ventricular ejection fraction. But our model actually does a better job of finding people who have lower risk when they have a defibrillator, both for sudden cardiac death, but also for all-cause mortality. So this again gives us more reassurance that we're finding people who are not only at high risk of dropping dead, but who would actually benefit from a defibrillator. Okay, a couple of implications of this work. One is we're going to try to turn this into a prospective study where we sample high-risk patients and some low-risk patients and follow them along and try to catch these malignant arrhythmias by doing continuous ECG monitoring. And eventually, if that goes well, I think building the groundwork for doing a trial of actual defibrillators in that high-risk group. But I think a broader implication that might be of interest to all of you is that we now have these tools, not just for ECGs or X-rays, but for MRIs and CT scans, where images can be turned into numbers. So here, an EKG can be turned into a prediction on the likelihood of sudden cardiac death. So it's an extreme dimensionality reduction technique, but it's a pretty useful one in a few different ways. One is, for example, now you've got every time someone gets an ECG, you've got a risk of sudden cardiac death. And so you can use that number as the dependent variable in a regression in a way that you cannot use an EKG or an X-ray or the image itself. But you can use that to look at a bunch of drugs and see, oh, this drug, when people start it, their risk of sudden cardiac death goes way down. Or this one, when they started, it goes way up. You can enroll patients in randomized trials based on this number, which is something we plan on doing. You can use this number to run smaller and faster randomized trials. So rather than waiting 10 years for an outcome, you can do an EKG and randomize people to drugs or controls and see what that drug does to the surrogate outcome, not as a definitive trial, but as a way of seeing, okay, if I have a drug, what other effects does it have? You can imagine this also for population screening, but you can also imagine now that we can collect a bunch of these data, like electrocardiograms, outside of the hospital, it opens up a ton of new possibilities for new device treatment combinations, even for consumer products. So I think the implications of this stuff are really, really huge for the healthcare system as well as for the research enterprise. And I want to maybe skip over this, except for commenting on the data. So I think one of the major roadblocks that I'm sure all of you have experienced is it's really annoying to get data. And I think that's bad for everyone. It's bad for researchers. It's also bad for hospitals because I think that the data business is going to be a huge part of what hospitals need to do to stay alive over the next 20 years. But hospitals are largely being consumers of AI rather than producers of AI. So I wanted to mention two entities that I helped set up. One is called Nightingale Open Science. So this is a philanthropically funded nonprofit effort where we work with health systems to build up interesting data sets of images linked to longitudinal patient outcomes. There's a data set on knee pain that we made with Judy Jachoya at Emory. There's a data set that I mentioned from Taiwan on sudden cardiac death. And all of those data are freely available to you or to anyone else who wants to sign up on the Nightingale Open Science platform. I also helped set up a for-profit called Dandelion, which has built a consortium of non-academic health systems and pooled all of their data with a heavy focus on imaging and waveforms and things like that, and makes those data available to companies and life sciences, AI startups that want to build interesting products based on the data or improve, for example, the efficiency of their clinical trial operations based on these kinds of real world data. Okay, back to the science part. I think one challenge, like when we're working with knees, it's pretty easy to like, you see a knee, you're like, okay, I can relate this thing to a knee. I can come up with some simple physical models of what knees do and where gravity points. And I think that can, without any more AI, lead to a bunch of progress. Electrocardiograms are harder because the heart is, with no offense to the knee, much more complicated than the knee. And so going from that ECG prediction to some level of understanding or abstraction of this problem is much harder. So let me, and you can run the interpretability playbook, but that's just going to tell you, again, where the model is looking, not what it's seeing. And so here's this interesting use of generative AI that we came up with for this model. So we've got our predictive model that can go from an ECG to a prediction on sudden cardiac death. In parallel to that, we train a generative model that can just encode an ECG into some latent space that can create new ECGs. So we take an ECG and we basically compress it into this latent space in a way that can reconstruct the ECG. And then we can use the predictive model to look at the risk level in that latent space and move around in it, and specifically to follow a gradient of risk up or down, starting from one patient's ECG and tweaking it progressively until it gets higher and higher risk. So here's an example of that. So the actual patient ECG is in purple, and the counterfactual high-risk ECG is in orange. And I think one of the advantages of this is when you just compare the ECGs of people who died to people who didn't, ECGs are really complicated. They're high dimensional, and the curse of dimensionality applies in the sense that there are lots of differences between any two ECGs from any two people. And it's really hard to zoom in on the stuff that's linked to the risk of death or not. But what this does is it zeroes out a bunch of that other variation, and it just tries to draw our attention to where the differences are that convey risk information. And that helps us build hypotheses. And I want to demonstrate that by zooming in on this one lead. So all these things, for those of you who don't care about ECGs, they're just looking at the electrical field produced by the beating heart over time. That's the x-axis. They're looking at the voltage from different angles. And so this is looking at the heart from one angle. And I just zoomed in on that thing. And the only thing you need to see, you don't need to know anything about ECGs to see this, but the actual low-risk patient in purple has a nice and spiky voltage change. When we change that to high risk, it starts off nice and spiky, but then it sort of peters out. And what we can do is translate that qualitative observation into a quantitative feature where we just calculate a metric of like the first difference and the second difference of that waveform over time. But that's something you can calculate in any ECG anywhere in the world. And what we find is that that new feature that the AI has shown us actually predicts sudden cardiac death in Sweden, in Taiwan, in California. And it's not hard to see. Like, this is not subtle. You can see the difference even if you've never looked at an ECG before between the high risk ones on the left and the age and sex match control on the right. It is not hard to see that slurred downstroke. You can see it, and I can see it, and I'm not great at ECGs. But until the AI pointed it out, nobody had seen this before, despite looking at ECGs for signs of sudden cardiac death for many, many years. And so I think this is a really nice example of how AI can help us see. And it can also help us build hypotheses, because now we've got this model that goes from an empirical finding in the world to a waveform. But the model has nothing to say about the cause of that waveform. The model doesn't know this is an electrical field. It's just a squiggle. But we've got a lot of computational models that can go from first principles of cardiac electrophysiology to that same waveform. So now that waveform is a common language where these two models can speak to each other, and where you can actually potentially tie empirical facts discovered by machine learning models all the way back to physiological primitives. And so I'm going to show you one just hypothesis that is probably not true, but it's kind of interesting, which is that one reason that you can think of for why something would start off very spiky, but then peter out over time, is scatter. So imagine just a wavefront hitting an obstacle and then hitting more obstacles. It's going to scatter. And because of the angle at which you're looking at that wavefront, that means from certain angles, it's going to get more orthogonal to your point of view. And what we find in the small number of patients who had cardiac MRIs is that the high-risk patients, and only the high-risk patients, have this high prevalence of late gadolinium enhancement on their cardiac MRI. And that's very consistent with subtle diffuse fibrosis, which is exactly the kind of thing that could scatter an ECG waveform. The problem is there are a lot of false negatives on MRI, and actually what you need to do is an endomyocardial biopsy. Like, you need to take a chunk of the heart out and look at it under a microscope. And I think that's one of the reasons that this phenomenon has been understudied, because it's really hard to study. And also why cardiologists don't really put a lot of weight on this finding. We looked at the notes of all of the patients who had this finding on their MRI. Not a single cardiologist mentioned it, not once. So anyway, this is just one example of how the AI system can point us to new interesting hypotheses that we can then follow up, which is something we're in the process of doing. So I think if you go back to that old cycle of medical discovery, from bedside to some machine-generated data about the patient, we run up and very quickly into the computational limits of the human mind for processing those complex data. And that's why we end up with a model that doesn't really get us interesting bench to bedside discoveries, and why bench has become so prominent, because there at least we've got theories about what genes do and what proteins do and how they translate into lots of important outcomes, and we can do clinical studies. But as we all know, a lot of things that work in test tubes or in mice don't end up translating very well back to the bedside. And that's a traditional problem with these models. I think today, even when we think about translating from the bedside down, doctors are so pressed for time today that very few people have time for the careful, curiosity-driven studies that people did in the past. And so I think this model has been blocked on multiple dimensions. And what I hope I showed you today is two glimpses of how that pathway can be unblocked by AI. So in the knee, we can use AI to point us to interesting new models based on physics and quantification around strain and loading that can lead us to test hypotheses around reducing load. In the heart, we've got grounding in electrophysiology that can give rise to different kinds of hypotheses that we can correlate to biopsy findings, do prospective studies, eventually translate that into studies of defibrillators. And all along, we've got this idea of surrogate outcomes, which is that now that we can fit images into a regression, we can make huge progress in lots of areas of investigation that we couldn't do before because we couldn't fit X-rays or ECGs into a regression before. So I think this new cycle is really, really exciting because AI is going to help doctors see better. And that's going to create these new abstractions at a level of abstraction that we haven't worked on in a while. And those abstractions, I think, can have really, really useful inputs from other fields, from computer science, even from economics, behavioral science, and engineering, that can translate back up into the bedside and cut down that huge failure rate for therapies that today start in the bench. So let me end there and would be really happy to answer some questions with however much time we've got left.
That was fantastic. Thank you so much.
Thanks,
A lot of
Emily.
really great information there. We do have a number of questions in the
Oh, great.
Q&A. So,
okay, let me just quickly scan through here. Okay, a lot of questions about the, let me try to just work through these. So Shanishka, you asked, is the radiologist report distinct from the diagnosis of arthritis? And I'd say that in clinical research studies, what the radiologists do is this super detailed quantitative evaluation of every part of the knee, and that turns into the Kellgren-Lawrence grade. In practice, people don't do the research grade stuff, and so they assign a diagnosis of arthritis that's a little bit more qualitative. And so we have the benefit of using these super detailed clinical data that are a more detailed version of what diagnostics people use in the clinic. Jose asks about the pain score subjective variation from person to person, which is a huge issue in working with pain scores. And I think that's why this approach is actually so nice, because what we're doing is we're taking that pain score with all of its subjectivity and saying, can we predict it with these pixels? And so this doesn't take away that subjectivity, but that predicted pain score is effectively the fraction of that total pain score that can be linked to pixels in the knee. And so it's actually sort of an objective version or an objective subset of that total pain score, because it's the part that's predictable, not with any subjective factors about the patient, but with just the image. And so I think it's a really useful new way to study and to break that pain score apart into the objective component and sort of like put all of the subjective thing in the residual effectively. Martine asks, is it always arrhythmia that makes people drop dead? No. And that's one of the things that makes this so hard to study. So, there are pulmonary causes that make people, so if you stop breathing, for example, from a drug overdose, opiates being one of the more common causes recently, sadly, that can produce sudden cardiac arrest. That has nothing to do with an arrhythmia. And so that's why this data set from Taiwan was so useful, because what they did in that data set is they bucketed these deaths into different causes. And they did that by going to talk to the family members that were there when it happened, the ambulance drivers. They followed patients along in the hospital. So they did super detailed studies to try to figure out what was pulmonary or a massive stroke and what was an arrhythmia. And our algorithm was very specific to the arrhythmic deaths rather than all those other deaths. Boris asks, what are diagnostic test performance indicators? And so, yes, the outcome rate is effectively the positive predictive value, because what we're doing is saying, here is a high-risk group. In other words, test positive. What is the outcome rate in that high-risk group? What's the yield? But that's effectively that's the same thing as positive predictive value. And all the other metrics we can also calculate, and they are going to be in the paper that will hopefully eventually be published. Boris asks a number of other questions. Heart rate variability is an interesting one. It is not a great predictor of sudden cardiac death, and I think just empirically in terms of all the metrics that you mentioned, one of the I think there's a general problem that speaks to, which is human interpretation of complex data is really hard. So we can hone in on some of the bold signals like, oh, like this rate is variable. But a lot of the things that that the algorithm is seeing are a lot more complicated. And empirically, when we include heart rate variability, just in a regression of sudden cardiac death on controls plus that, it's not a very good predictor. Okay, Hajira asks, what about incorporating assessments done by PT and chiropractors? This is a great question. And in fact, when I described to a friend recently the research that I was doing on the knee, my friend said, oh, so basically you're becoming a chiropractor. And I think that was a very good take because I think that chiropractors and PTs actually have really good intuitions about the root causes of problems because they don't just look at where you're hurting. They look at, oh, you have this asymmetry over here and that's straining over here and that's doing. And so I think that those kinds of assessments are really, really useful and those intuitions are really good. I think that in general, those don't get written down. And so they're really hard to do data analysis with. But I think it would be fantastic to get those kinds of assessments written down and incorporated into these kinds of this research program. And then the last question is, are there important considerations for models for more complex diseases like cancer? And is stratification of I see. I'm not quite sure if I understand the question, so feel free to type more. But I think that complexity depends on the level of abstraction. And so cancer is really, really complicated on a lot of levels, but sometimes it's just there's a one mutation and that turns on or off a pathway. And if you shut down that pathway, you fix the problem. And I think that's a great illustration of how attacking problems at the right level can be super, super useful. But not all problems, unfortunately, are reducible to one gene or one protein. And I think that's disproportionately the problems that we have left. Do you think any clinical diagnostic or severity criteria should include a description about how it was created? Yeah, absolutely. It's a great question. And I think a lot of people are working on, these like nutrition fact sheets for models. I think one really important thing that should be on those descriptions is what is the literal outcome that a model predicted? I think it's often very hard to figure that out when people are telling you like, oh, like I have a model that predicts depression. It's like, really? What do you mean by depression? And often it's like a model that predicts an ICD code for depression that was generated in the course of an interaction for clinical care that was paid for by a payer. And that sounds a lot less interesting than a model that predicts depression. But I think it's really important to know that you're predicting a billing code rather than a clinical diagnosis. And so I think that's the kind of information that should be on those descriptions and really foregrounded. And I'll add that a lot of the research that I've done on where algorithms go wrong in terms of creating racial bias and other problems is because you think you're predicting one thing, but you're actually predicting another thing. And so the example that I worked on most is an example of algorithms used for population health management and for figuring out who needs help with their health that actually predicted how much patients were going to cost. But because of barriers to access, some patients cost less than others, not because they don't need help, but because they face barriers to access and discrimination. And so the algorithm saw accurately that some patients, for example, Black patients or poorer patients, cost less. And it used that to deprioritize them for access to care, even though they needed more care, not less care.
Yeah, those are all very important considerations, and it's a lot to think about when you're building these models and thinking about what data to collect and what model to apply.
Yeah, and I think that it's absolutely, it's like, especially for this audience, I think it's you'll appreciate it how hard it is to come up with the right outcome for a model, and why I think for these population health algorithms, option one is, man, there's a lot of data on comorbidities and like what is health? Like there's no variable called health. So you have to stitch it together from all these different sources, and it's really annoying, and lab values and vital signs and diagnosis. And option B is like, oh, there's this variable called cost. And it's already been cleaned. And when it's missing, it equals 0. And so it's very appealing to just predict cost because it's easy and it's reasonable. Sick people do generate costs on average. But there are these things that make cost a very bad proxy for health, especially for people who face barriers to access.
Yeah, and people who never even show up in the data set, right? Because they haven't even been seen by a
Exactly.
healthcare provider. So
Exactly.
interesting problems and important to be thinking about. So thank you for sharing your thoughts with us.
Oh yeah, thanks for the invitation. This is a fantastic conference.
Great. And so I think we'll wrap up there. I just want to let all of the participants know that you will have to go and join a separate session for each of the talks. They're all pre-recorded, so the video will start playing right at the minutes of the start of the talk, and then there will be a live session for questions at the end of each video if there's any time remaining. So thank you, Ziad, for being here. Have a great day, and you're welcome to join any other talks the rest of the conference. We'd love to see you
so
there.
much.
And
Awesome.
for everyone else, we'll see you in the next lineup of talks.
Okay. Thanks again.
Bye.
Bye-bye.